This video will be the first video in 3 parts for 13.1. So 13.1 spans about 19 pages, so we're going to do it in 3 different sections here. But on all of it, we are finding an area, and specifically it's going to be an area underneath a function. So we start off with some geometrical shapes that we should be familiar with. So velocity time graphs, if you took physics, that should be another concept that's familiar to you. But the graph shown below is a velocity time graph for the journey of an object. The time taken from the start of the journey is represented on the horizontal axis, and the velocity of the object is represented on the vertical axis. So time is here, velocity is the y-axis. This object travels at a constant velocity of 8 kilometers for 4 hours, and then it travels a further 2 hours with a steadily decreasing velocity until it reaches 0. So here's the constant velocity there, and then it starts to decrease all the way until it hits 0. And then the question is, what distance did this object travel during the entire journey? So if you think about it, if an object is traveling a certain velocity over a certain amount of time, that is going to give you the total distance that it travels. So this green shaded box right here is just a box of 1 unit by 1 unit. So that's 1 square kilometer in this case. And if we could find all of the area underneath the curve, then that's going to give us our total distance. So the way that we start in 13.1 is by using some shapes that we know how to find the areas of. So in this case, we'll see in just a second, it gets separated into a rectangle and a triangle. So let's check that piece out. All right, so it goes into 2 different pieces, the constant part and then the decreasing part. So in this diagram, we're just finding the total area of this rectangle and not the triangle at this point. So what's the width of that rectangle? It's 4. What's the height? It's 8. So the total area is just the length times the height, or the width and the length, and that is 8 times 4, which is 32. So the area under that part of our function is 32. Okay? Down here, this is now, the shaded part is the rest of it, which is this triangle, and we know that the area of a triangle is 1/2 the base times the height. So again, 1/2 times the width, which is 2, and the height is 8. So 1/2 times 2 times 8 would just give us 8. All right? So the area of the rectangle is 32 here. The area of this triangle portion is 8. And 32 plus 8 gives us 40. In this case, the units are kilometers, and that's our total distance. Okay, so the area under that curve, 2 geometrical shapes we know, a rectangle and a triangle, would be 40. All right, so then we have a similar question, but let's see what's different about this. It says, now if the velocity time graph was a curve, how would you calculate the area? So that's the question we're leading up to. They ask us here now, but we still get some non-curved pieces. So we'll study different methods to find or approximate those areas between the graph of a function and the x-axis. That's where we stay the whole time. All right, so this question here says, for this velocity time graph, find the distance traveled. So it's a similar question, but you have no axes labeled. So there's nothing on the x, which in this case it's time, t, or the y, which is the velocity here. There's nothing labeled. We don't know that point of intersection or that point of intersection. But just because it's labeled doesn't mean we can't find it. So if we are looking at this line, we have this equation for the line. We know that if we put this back into slope-intercept form, this would be y equals mx plus b. And b, the 10, is the y-intercept. So right here, that would be a unit of 10 in the velocity direction. All right? On the x-axis, which is t, then we're just trying to find out where that line intersects the x or t-axis, and that would just be when the function is 0. So we can replace the function right here. We'll just put it in right here. We want to know what's the value for t when the function is 0. So 0 is equal to -5t plus 10. All right, we're just going to solve for t, so subtract 10 from both sides. That gives us negative 10 is equal to negative 5t. And then to get t by itself, just divide by the negative 5. And we get 2 is equal to t. So we now know that it intercepts the x, which is t in this case, axis at 2. All right, so if we want to find the total distance traveled under the velocity curve, again, we're just finding the area beneath here. So this is another triangle, so the area here is just going to be 1/2 the base. What's the base? It's 2 times the height, which in this case is 10. So 2 times 10 is 20, half of 20 is 10. And so in this case, this time it's measured in meters per second. So the area under the curve is 10 meters, which gives us our distance. So our total distance traveled in this situation would be 10. Okay, so let me just take this away, and then we can just show how the textbook does the exact same thing. But we're going to see that it's the same value there of a total distance of 10, but they have that shaded in. So found the y-intercept or velocity to be 10, the x-intercept or t to be 2, and we just found out that the area was 1/2 10 times 2, which gave us the 10. So that is our distance, total distance traveled. Okay, so in a similar example, we have this question, and this will get us through exercises A. But now we have another 2-part area. This first section is a triangle. The second section is a rectangle. What we don't have is this right here, this x value. So what's that width? And therefore, what's that width? So we need to find where these two intersect, okay? And again, that's pretty easy. Here's the equation for this line, 1.5x. We want to know, when does it equal 3? So we can just say, okay, when does 1.5x equal 3? If we're going to solve for x, we can divide by 1.5. And that gives us x is equal to 3 divided by 1.5 is 2. So that tells us that right here is 2. So that x value is 2. Okay? Once we have that, we can find what we need. So same thing. What's the area of this triangle? Well, it would be 1/2 the base. Now we know the base is 2 times the height. What is that height? It's this y value of 3 right here. So 0 to 3, that's a height of 3. So 2 times 3 is 6. Half of 6 is 3. So this triangle has an area of 3. Now we do the same thing with the rectangle. So now the rectangle, it's just base times height, or length times width, however you want to view that. What's the width of that rectangle? It goes from 2 to 5, so that width is 3. What's the height? It's also 3. So the area of that rectangle is 9. So that area is 9. So then our total area would just be those two shapes combined, 3 plus 9, to get us 12. Okay? And in this case, we don't have any units, so we just say find the area under the graph. It would be 12 units, whatever those are. But if it's not labeled, we can just say units. Okay, so that is enough for you to answer exercise 13A. So check out the questions for that. But let's move on to the second section, which would give us the information needed to get us through 13B. All right? And here is the first time that we see some notation for what's ultimately going to be called finding an integral. Okay? So I'll just read this. When f, the function, is not negative on some interval a to b, a little bit hard to see here, but a is this lower bound is what it's called, and b is the upper bound. Then f of x dx gives the area under the curve from A to B. All right? And this right here, the integral from A to B of f of x dx reads as the definite integral between A and B. The number A is called the lower limit or lower bound, and B is called the upper limit. So if I wrote that slightly, so similar, but let's just break it down. So A would be the lower bound. We're going to start to see this more and more. So A is the lower bound, or the first value, and then B is our upper bound. Okay, and then we have the function f of x, so whatever that is, it's going to have an equation, but this is called the integrand. So whatever the function is, that's called the integrand. And then there's always this notation, the dx. Okay, so the variable for which we're taking the integration of is just there. So if this was f of t, we'd say dt. If this was f of s, it would be ds. So this is the variable of integration. And that's just a bit of notation there. Okay? But we're finding the area under whatever f of x is. Okay? And then everything that's written in black is called the integral. So this is the integral of f of x from A to B, is how that's often said. And there's a picture here. So if this is A, this is B, and that's the function f of x, we're finding this shaded area that is in green. So ultimately, that's what we're doing. So IB puts it here. It's a little bit early, in my opinion, to put that notation, but it's always good to see it. And like I said, we're going to see it more and more. So that's going to be notation we want to be familiar with. That is, in fact, what it is we're doing. Okay, but we're going to keep for a little bit with some geometrical shapes that we know. So write down a definite integral that gives the area of the shaded region. Find the value of the definite integral. Okay, so here's our picture. And so they want us to write the integral. So here we go. That's the symbol for the integral. What's our first bound? What bounds us on the left side? That would be the number 1. What's the upper bound? That's 4. Okay, what's the function? Well, it's labeled here as negative x plus 6. So you could put that in parentheses to say that's the whole function. And we're taking the derivative with respect to x. Okay, so that would be how we would write the definite integral. The definite meaning it's defined on certain values a to b. In 13.2, we'll see indefinite. Okay, so that's what it is we're asked to do. For now, the way that they want us to view this is a trapezoid, and the formula for a trapezoid, to find the area of a trapezoid, is 1/2 the two bases, sometimes labeled base 1 and base 2, times the height. Okay, so again, using a geometrical shape, just like we did a rectangle and a triangle previously, we can use a trapezoid, or it is possible we could cut this into a square and a triangle. That would work as well. But they want us to view this as a trapezoid. For right now, most linear functions, that's what that function is, can be broken down as a trapezoid. Okay, so if we were trying to find that area of the trapezoid using this formula, it would be 1/2 base 1. Doesn't matter which one you consider to be base 1 or base 2, but this is base 1, that's base 2, or vice versa. But what's that base? It goes from 0 to 5, so that would be 5 plus base 2. What's this base? It's 0 to 2, so that base is 2. And then times its height. So we've kind of flipped this 90 degrees. We said this was a base, this is a base, so the height is right here. It's from 1 to 4, so that is 3 units there. All right, so you could do this in a couple ways. You could say 5 plus 2 is 7, 7 times 3 is 21, 21 times 1/2 is equal to 10.5. So the area under this curve would be equal to 10.5 or 10.5. Okay? So that's the way that we can do that, using it as a trapezoid, or like I said, we could have split that one into a triangle and a square, and that would work as well. But you can see that they chose to do it as a trapezoid. They get the same answer that we did right there, and they're finding that total area underneath that to be 10.5. Okay, let's do a similar one to that, but this time we don't get the picture given to us. So now it just says, for the definite integral, so now they've given us an integral of the function x plus 4, state clearly the function being integrated. Okay, well, the function being integrated is that x plus 4. The lower limit of integration and the upper limit of integration. Here's your lower limit, that's the -1, so our lower limit's -1. The upper limit is 3. Okay, so to answer question A, it's just asking us, can we break down the components of an integral? And again, that's our function of integration called the integrand, and then the lower limit and the upper limit. Okay, it says sketch the graph of the function, shade the region whose area the definite integral represents. All right, so we're making a sketch, so let's make an xy axis. I know it's only going from -1 to 3, so I might just label -1, 1, 2, and 3. Okay, I don't care about anything beyond that. Those are my limits of integration. And then my function is x plus 4. Okay, so again, this is a linear function with a y-intercept of 4. So it's going to hit the y-axis at 4. And then what's the slope? It's just 1. So I can go up 1, over 1. And I can do that all the way across if I need to. And I can go down 1, left 1 right here. So yes, this line continues technically infinitely beyond that. So that would be my sketch. But I'm trying to shade the region that the definite integral represents. Well, it's going from -1 to 3. So this right here, if I was shading that, this would be the area that we are finding between -1 and 3 underneath that curve. Okay, so then it says find the value of that. Again, we could view this as a trapezoid with this as one base, this as another base, and that would be the height. So let's just set that up again. 1/2, base 1, if this is our first base, well, how high is that? It's 0 here. It goes up 1, 2, 3, so that base is 3. Plus, here's our second base, it's 0 all the way up to, so that was 4, 5, 6. So this would be 6. All right, hold on, 4, 5, 6, sorry, I drew that in the wrong spot. This should come up to right here. Got a little crooked on there. That is our area of integration. So we went up 3 different slopes. So we were at 4, go up to 5, from 5 went up to 6, from 6 we went up to 7. So this has a height of 7. And then what's its base? Well, what's the height? It's from -1 to 3, so that is a distance of 4. And so 4 is our height. So base 1 plus base 2 times the height. So this is 10 times 4, which is 40, and half of 40 would be 20. So our total area, again a trapezoid there, would be 20 units in this case. Okay, so that will get you through exercises 13B. So 13B focuses largely on the fact that if you integrate underneath a linear function, you're going to get a trapezoid, and you can just use the fact that you know the area of a trapezoid is 1/2 the 2 bases added together times the height. All right, and then we kind of switch gears a little bit, and for section C of 13.1, we get to use the calculator for the most part. So it says calculate the definite integral from 0 to 2 of x squared plus 1, and then dx is our variable of integration. So notice here, this is now not a linear function. This is quadratic, this is a parabola. So if you were going to visualize this, we could graph it on a calculator, but if we're just visualizing this, it's a parabola centered at 0, 1. It's just shifted up 1, okay? And they want us to find it from 0 to 2. We'll learn some strategies to do this by hand, but for now, they're just wanting us to use our calculator to do so. So this is the integral from 0 to 2 of the function x squared plus 1. And the way that you can do that is on your calculator. So if you go there, you can hit the math button right here. So math. So right here is where my cursor is, math. So hit that button, and then you see this menu. And if you look at these, right down here at the very bottom, this stands for function integration. So your calculator can actually find a numerical value for many functions. So we're going to select choice number 9. All right, and as you see, it sets us up an integral, and what we need to put in is the lower bound, the upper bound, the function, and the variable of integration. And for your calculator, you're just always going to use x, okay? So 0 here, 2 here, from the question they gave us. Remember, the function was x squared, and then plus 1. And then you just want to put the variable of x right there, okay? And when you do, you can hit enter, and it gives you that value of 4 2/3. Go ahead and set it right here, okay? So 4 2/3, so 4.6 repeating would be 4 2/3, and so the area under the curve for that function would be just this value right here. So that would be, if you're allowed to do it using just your calculator, don't even need to show much work at this point, that's how you could set that up, all right? So if we go back to here, right, our answer here, we would just say, okay, we put that into our calculator and we got 4.67 or 4 2/3. Okay, so then, example 6, similar question, we just have a little bit more work to do to get what we need. It's not just explicitly given to us with the upper and the lower bound. So this time it says, consider the region A enclosed between the curve y equals negative x times x minus 3 and the x-axis. Okay? Write down the definite integral that represents the area of A, and then find the area of A. So here we go. We can do the following. We need an integral. We need a definite integral. What we don't have is a lower bound and an upper bound. Okay? We do have the function, so we can say this is our function, and all of that is multiplied by dx. So we have the function. We don't have these areas of upper and lower bound. So this is true. It is true. We could have seen the function like this. Negative x times x would be negative x squared. Negative x times negative 3 would get us plus or positive 3x. Okay? So it could have been written this way as well. But it was given to us like this, and that actually does us a favor, because if we want to find the area between the curve and the x-axis, well, we just need to know when does the function equal 0, and that's when it's going to intercept the x-axis. So here's what we have. We are just saying, okay, when does negative x times x minus 3, when is that equal to 0? All right, think about this as like when you were factoring a quadratic. What value of x will make what's in parentheses equal to 0? Well, that's 3. And if that's 3 minus 3 is 0, then 0 times whatever this is, which in this case would be negative 3, is still 0. Okay, but the same thing happens here. What value for x will make negative x equal 0? So what number can you put into negative x to make it 0? Well, that is 0. So the two places that will make the function equal 0 are 0 and 3. So that's where it intercepts the x-axis, which is what gives you your bounds right here. So we know that the lower bound, you just pick whichever one's the lesser of the two to be your lower bound, comes first moving left to right, is 0 and 3. Okay, so that accomplishes A. Write down the definite integral that represents the area of A, And then now it says find the area of A. Now that we have this, knowing what we just learned from the calculator, we can find that value by just plugging it in. So I'll leave that right there. Let me change my screen and hopefully we can see what we need to. So now we're here. If I clear that out, okay? So I'm just gonna put in what I see right here using Math 9. So again, I'm gonna hit Math 9, which will give me function integration. So Math here, down to select 9. It pulls up this integral, okay? And I just put it in, 0 and 3. So 0 is the lower bound, 3 is the upper bound. Okay, let's just type in that function, negative x, and then times, so right here, negative x, and then x minus 3. So negative x, got to do it on the calculator here, and then times x minus 3. And I'm going to change this to be the calculator negative, just so it knows what we're doing here. Okay, so I put that there, and then I do need to say that it's dx. So get over to there, and dx. Okay, I have this is what's right there, so now I can just hit enter, or equals, and it's going to calculate the area underneath that curve from 0 to 3 for us to be 4.5. So this is equal to 4.5. All right? So same idea. The only difference is we did not have our limits of integration, so our lower bound and our upper bound, to write out the integral. We needed to remember that, okay, what x values would make our function 0, get us those bounds, and then once we had it, we could get the value. Okay? That will get you through exercise 13C. So you should be able to do 13A, B, and C now. That's kind of the introduction to integration, and we'll keep building off of that.